Alright, this is a video where we are going to do as many examples as possible in the allotted time to determine whether that molecule is aromatic, anti-aromatic, or non-aromatic. A very classic exam problem. Before we do that, let's one last time go over the rules to determine whether a molecule is aromatic. And I'll do this in blue. I'm going to try to color code this as best as possible also. 1. Maybe it wasn't apparent in my previous videos, but an aromatic molecule should have a ring in it. It should be cyclic. So it's a ring molecule with all ring atoms sp2. That's rule number 1. Number 2, the ring is flat. And number 3, it has the Huckel number of pi electrons. I don't like memorizing that formula. It's called the Huckel rule formula or the Huckel number formula. I just like to remember the number of pi electrons can be 2, 6, 10, 14, etc. You just add 4 after you have 2. Okay, so that's benzene, right? If you need to quickly recall what is a Huckel number, 6 is a Huckel number because benzene has 6 pi electrons. And just add 4 to that, 10, another 4, 14. Okay? Anti-aromatic. Number 1 and number 2. You follow 1 and 2 for the aromatic, so I'll put check, check. But for 3, you have a non-Huckel number, or you could say you don't have a Huckel number of electrons, Huckel number of pi electrons. That could be 4, 8. There are instances where it could even be an odd number. If it doesn't fit Huckel's number or Huckel's rule, then you might be anti-aromatic if you can fit rule number 1 and rule number 2. So non-aromatic is everything else. And how do we get a non-aromatic molecule? By violating either rule 1 or rule 2. So you could say everything else. And typically, you violate, or you don't follow. Let's not use the word violate. You typically not follow all sp2 in ring or flat. And again, that's not follow. So if you have an sp3 carbon in the ring, automatically non-aromatic. If your ring is not flat, automatically non-aromatic. Okay. Let's do our 3 main examples, and then we're going to branch out. First one is benzene. Hopefully you know that that is aromatic. Next one was cyclobutadiene, anti-aromatic. Okay. And the rule that we're using here is that if you have 5 atoms or less in the ring, you are considered flat. Okay. If 5 or less atoms in ring, you're automatically flat. The molecule is automatically flat. Because, take a look at this, cyclooctatetrene. Yeah, let me do this in green. let's do our rules. Every atom is sp2. Check. It looks flat the way I drew it, so we're not going to have a check, but right now we're going to say it looks flat. Definitely it has 8 pi electrons. Check. By using all of this, we're going to say it appears what? It appears anti-aromatic, right? It's all sp2 atoms in the ring. The molecule can be flat, or is flat. And 3, we have 8 pi electrons. That's not a Huckel number. So right now I'm going to say it appears, or it seems, anti-aromatic. But what do we know about this molecule? Because it's large enough, it's more than 5 atoms, and because of our stability trend. This is from the previous video, 13C50, that anti-aromatic is worse than being non-aromatic in terms of stability. So if the molecule can conform to get out of being anti-aromatic, then it will. 8 atoms is enough to do what? It's enough to do this. And now it's not flat. Our ultimate conclusion is that this is non-aromatic. Okay, so let me circle all our answers. Aromatic, anti-aromatic, and non-aromatic. Initially we thought it was anti, but realized that the ring is big enough that it could pucker to get out of it being flat. Okay. What molecules can we do next? How about charged molecules? Okay, and we'll start tiny. Let's start with this one right here. Positive. Okay. So what's our analysis? Our analysis is, we know that carbocations, do you know what hybridization carbocations are? Carbocations are sp2. It has an empty p orbital. So this is sp2. That is irretractable. It's always sp2. So we should put a little note here. All carbocations, all carbocation carbons are sp2. Okay. We have 2 other sp2 atoms here, and that makes a triangle. What else do we know? It's flat, right? Because it's less than 5 atoms. And how many pi electrons do we have? We have 1 pi bond made up of 2 pi electrons, so there are 2 pi electrons total. Do you see what our conclusion should be for this molecule here? This is a cyclopropenyl cation. sp2, all atoms are sp2 around the ring, flat, 2 pi electrons. 2 pi electrons fits the Huckel number. This is aromatic. That's our conclusion. Okay. What about the anion version? Okay. What would the anion version look like actually? Let me do this on the next page. Do you see why you have to be also very good at not only formal charges, right, but knowing that the carbanion has a negative charge on the carbon. So how many bonds does this have? It still has 3, right? We have a hydrogen here. Just like for the carbocation, it's 3 bonds and no lone pairs. If you want, you can put a hydrogen there if you want. Okay. I know the angle's kind of screwy. It should be straight up because it's trigonoplanar, right? But I put the plus charge right there. Well, Okay. What I would do first is I would actually look at, well, it has to be flat. That's, I think, the quickest thing that we could decide because it's less than 5 atoms, um, 5 atoms or less. How about pi electrons? This is interesting. Um, so on the surface, we have 2 pi electrons, or it looks like we have 2 pi electrons for this pi bond. That puts me in the aromatic bucket, right? We have flat, we have 2 pi electrons. It looks like we're headed towards aromaticity. But the thing is, this atom here is sp3, okay? And we're going to say sp3 because if you've done hybridization with me, we count balloons. And the balloons are 1, 2, 3, 4. This is debatable, okay? Because I actually want it to be sp3. Okay? If this was sp2, if this was sp2, we would automatically put the lone pair in a p orbital. We would have to. That's the only place it would fit. And if we put the lone pair in a p orbital, then we would have 4 pi electrons, and this molecule would be anti-aromatic. For this specific case, okay, we're going to quote unquote keep this as sp3 because in other cases we will have a chance to put this in an sp2, um, have this sp2 hybridized. Do you know why I say that? I could prove it to you actually. Because what if we forget about the cyclopropenyl anion? What if we had this? If I gave you this molecule, that's an allylic carbanion, and you could have this resonance. Okay, so we're going a little bit back to talk about allylic systems. Okay, but how does that happen? That has to happen because that carbon has to actually be sp2 hybridized. We know we have 2 hydrogens, right, on both of these carbons. And we have a hydrogen, we'll just draw it off to the side. But look at this molecule here, sp2, sp2, and it has to be sp2 because we're moving those electrons to make the pi bond next door. So that would have to force it to be in an sp2 hybridization. And your 2 electrons are here. The lone pair is there. For this to resonate, maybe another way to say it, for this to have resonance, this has to be sp2. Even though it violates or it doesn't follow our balloon counting. A balloon, for the rest of you who are not in my class, is the area of electron density. And if you count the areas of electron density around this carbon, wouldn't you count 4? 1, 2, 3, 4. Typically, that would say that that molecule or that atom is sp3 hybridized, tetrahedral. But for us to do resonance, it has to be sp2. The thing is, okay, if we choose to have this participate in resonance, then that would have 4 pi electrons. So here's what we could put on paper. If the carbanion carbon is sp2, okay, then there are 4 pi electrons. You are counting those 2 electrons if the atom is sp2. Just like here, you're counting, see how there are all these dots are in p orbitals? So that has to be part of the pi system. This has to be part of the pi electrons. Now this could happen. See, this has nothing to do with aromaticity because it's not cyclic. Okay, we're not doing we can't do a Frost circle in this case. All right, but here it's cyclic, and we have to decide whether we want to count those electrons or not, whether this atom is sp2 or sp3. Let me finish this thought. If the C minus is sp2, for it to participate in resonance like this, then we actually have 4 pi electrons, and it's anti-aromatic. Therefore, what are we going to do? We're going to say that no, the molecule would rather have this hybridized as sp3. It's more stable as sp3. Because now that it's sp3, we violate what rule? Let's not use violate again. We don't follow that all the atoms are sp2. Therefore, our final decision in this is non-aromatic. Okay, not this molecule here. Tricky. It is definitely controversial because in older textbooks, yes, they call this molecule anti-aromatic. But in newer textbooks, and there was an article maybe, I don't know, maybe 15 years ago that had more experimental evidence that this molecule acts more like a non-aromatic molecule than an anti-aromatic molecule. Okay? Some textbooks don't even approach this. They kind of ignore this molecule and they say, well, this molecule is not aromatic, but they don't make a decision whether it's anti or non-aromatic. That is, a tricky one. That's a tricky one. Okay. I mentioned Frost circle. Okay. Let's go back and look at this molecule here. Okay. And let's take a look at the Frost circle. One more practice using this idea to use a circle to try to figure out where the energy levels are. So here's my circle. And remember the rule, when you have a polygon within that circle and you're using it for the purposes of figuring out the energy levels for the molecular orbitals, you don't put it on a square base, on a flat base. You make the bottom point. So there should only be one lowest, right? One lowest molecular orbital. And you're just drawing places for the electrons where the polygon touches the circle. Now the thing with this is that, oh, very interesting. The thing with this is that the non-bonding line is here. Remember the non-bonding line? It's the midpoint. Everything above is anti-bonding. Everything below is bonding. Okay, so this is interesting. We have a pi 1, pi 2 star, and a pi 3 star. But how many pi electrons do I have? I have 2 pi electrons. 1, 2. See, my conclusion here is that all the electrons are paired. It's cyclic. All the atoms are sp2 hybridized. All the electrons are in bonding orbitals. There are no electrons in anti-bonding orbitals. So this molecule, we've concluded on the previous page that it is aromatic. Okay? But this is the Frost circle for that molecule. Now imagine if we had an anion. We have 4, let's pretend that it is sp2, and we have 4 pi electrons. Well, yeah, where would electron 3 and 4 go? It would go here and here. Not only are they in anti-bonding molecular orbitals, but also they are unpaired. In the previous video, I mentioned that unpaired electrons are pretty unstable. Okay, but also in this case, if we put 2 more electrons here, both of them are in anti-bonding molecular orbitals. So that makes that molecule very unstable. The beauty of this is that an atom can change hybridization. You know it changes hybridization during reactions, right? When you attack a carbonyl group, the carbon is first sp2 and becomes a tetrahedral intermediate, sp3. Here it will, it it doesn't matter whether you think it changes to sp3 or it stays sp3. The fact of the matter is it's more stable as an sp3 atom because now we don't have to worry about it being anti-aromatic. It becomes non-aromatic. How many examples have we done? 1, 2, 3. The charged ones, 4. Oh, and here, the plus, 5. Okay, let's keep going. I forgot a very important uncharged one, actually. How about this one here? sp2 rule, check. Okay. Flat, maybe. Okay. How many pi electrons? How many pi electrons does this molecule have? 2, 4, 6, 8, 10. 10 pi electrons. Oh, that's a Huckel number. Check. So here, what are we going to say? It looks aromatic, and I'm trying to be a little bit trying to lead you on. I'm going to say it seems aromatic because, unfortunately, it can't be aromatic. You see why? It can't be aromatic because try to make this model at home. If you try to make this model at home, look at your hydrogens. Oh my goodness. They are clashing. They're bumping right into each other. It's impossible to make this flat. Everyone in my class should have models, okay? If you had before Organic Chemistry 1, make this model. And you tell me, can you flatten it? Can you make it flat? Because according to the bond lengths and the bond angles, that hydrogen is right on top of this carbon now. And this hydrogen is right on top of this carbon. It's impossible to make flat. So it's going to pucker. It's going to kind of twist. That's the only way it can exist, or else you'll have atoms trying to exist where other atoms are. Oh boy. If it's not flat, what category is this molecule in? This is non-aromatic. Look at our three non-aromatic examples. In each case, they have their own reason why they are non-aromatic. For the cyclooctatetrene, it's non-aromatic because it's getting out of being anti-aromatic. Because if it was flat, it would be anti-aromatic. So this is happening because it wants to avoid being anti-aromatic. This one too. This one is an sp3 carbon because it doesn't want to be anti-aromatic. Our last example, oh man, it wants to be aromatic. It looks like it has a great chance of being aromatic. But when you make the model, you'll realize that it's impossible for this molecule to be flat. It could still exist, it's just going to have those two hydrogens kind of splayed, one towards us and one away from us, but that's going to cause the molecule to be non-flat actually, because you're going to shift these carbons a little bit. So that's non-aromatic. Okay. All right. How many anti-aromatic molecules do we have so far? We only have one, the cyclobutadiene. Okay, so let me give you two more examples, and you tell me what they should be. These are going to be charged. The first one, let's make it minus. So there's a lone pair, and this is the second one. Okay. Whew. The first one. Oh, I'm not going to draw it, but can you see how this could have resonance? And for this to have resonance, you know we've discussed already that that atom has to be sp2 hybridized, just like we had for the allylic carbanion. Oops, I should put a negative charge here. Carbanion. Okay. All right. But is it beneficial for us to make this sp2? Because if by making this sp2 and by including these two electrons makes us anti-aromatic, then I don't want to do that. I'm going to go back and say, well, no, we're just going to count areas of electron density and call this sp3. So here's the exercise. And this is the exercise that you would want to do for your anions, okay? Because I'm going to label it actually right away. For carbocations, what did we say? All C pluses are sp2. This one has no chance. This has no choice, okay, except to be sp2. This one does have a choice because if you want to have resonance and resonance is a stabilizing effect, then it will be sp2. So this is your process. If sp2, the C anion, the carbanion, what is true about this molecule? Well, if that's sp2, then we have sp2, all the atoms are in the ring. Check. Okay, it's 5 atoms, so we don't even have to do much thinking about that. 5 atoms or less, the ring is flat. Beautiful. I don't want to be concerned about whether this molecule would do something like this. Okay? I don't want to be concerned whether the molecule does something strange like this. It's no debate. It's flat. How do you count the pi electrons now? If this is participating in resonance and you have a p orbital here because it's sp2, then that means that this lone pair is part of the pi system. It is circulating around the ring, just like benzene. Okay, so this is part of the pi system. So you are including both of those electrons, just like over here. Let's label this. How many pi electrons do you think this molecule has? By just counting the double bonds, you may think it only has 2 pi electrons. But you understanding that this participates in resonance, it actually has 1, 2, 3, 4 pi electrons. Okay? 4 pi electrons. So the idea here is let's first check whether we want this to be sp2 or not. And if it's sp2, we've satisfied rule 1, we satisfied rule 2, and we have 6 pi electrons. Check, check, check. These are the rules for a molecule to be aromatic. This is aromatic. Okay. It's not a huge deal. There's only one instance where you have to decide that hybridization, that hybridization can change. Okay, and that's when you have an anion. And you're going to pick whether it's sp2 if it's beneficial, because in this case, if that atom was sp2, it is not beneficial because it would kick me up to 4 pi electrons and I would be anti-aromatic. This one might be easier. Okay, so sp2, check. It's 5 atoms or less, flat, check. But now how many pi electrons do I have? I only have 4 pi electrons. This is our second molecule that we know of that is anti-aromatic. That was a lot for this video, but look at your notes as it stands. We've categorized, I'm checking my page 1, 2, 3, 4, 5, 6, 7, 8. We've categorized 8 molecules as either aromatic, anti-aromatic, or non-aromatic. Okay. We still have more to go because I haven't done any examples where we have oxygen and nitrogen within the ring. And that's going to complicate things a little bit because, both of those have lone pairs. And when we had a lone pair that was on an atom in the ring, in some case, well, not in some cases, in all the cases, we had to decide whether that atom is sp2 or sp3. Okay, so that's going to be a more challenging proposition when we look at atoms, when we look at rings that have oxygen and nitrogen in them. But thus far, I think this is a good start. We have 10 molecules now that that you know how to categorize, and with practice, whether from the textbook or the practice problems, you'll get good at this. Okay. Um, so the next video will be more examples, more practice.